Motion of charge in a magnetic field, Part 1. Objective: to understand the motion of a charged particle in a magnetic field. We know that the equation of the magnetic force vector Fb, which acts on charge q moving with a velocity vector v in a magnetic field vector b, is vector Fb equals q into vector v cross vector b. Its magnitude can be written as Fb equals qv b sine theta. Using the cross product. Here, theta is the angle between the velocity vector v and the magnetic field b. This equation tells us that if a charge moves in the magnetic field with its velocity vector v parallel to vector b, that is, theta equals 0 degrees, the magnetic force acting on the charge is 0. The same is true if vector v and vector b are anti-parallel, that is, theta equals 180 degrees. In both cases, the motion of a charge is not influenced by the magnetic field. Consider a freely moving positive charge q entering the magnetic field such that vector v is perpendicular to vector b. For this case, theta equals 90 degrees, and hence the magnitude of the magnetic force is maximum and is Fb equals qvb. To find the direction of Fb on the positive charge, we use the right-hand rule. Orient your first finger along the velocity vector v and second finger along the magnetic field vector b. The direction of the thumb gives the direction of the magnetic force Fb. This force changes the path of the charge in the magnetic field. At point L, the force Fb is perpendicular to v. This force bends the trajectory of the charge and it reaches M. At this point, the force pulls the charge inward, bending its path further, and the charge reaches the point N. The charge is acted upon by a constant centripetal magnetic force at every point of its trajectory. As the force is always perpendicular to its velocity and hence the displacement, the work done by the magnetic force on the charge is 0. The energy of the charge remains constant and hence its speed also remains constant. Therefore, the magnetic force merely changes the direction of the velocity of charge and not its magnitude. As a result, the charge performs a circular motion within the field. Since the charge is now held, we say that the magnetic field can trap the charged particles. The above fact is true for the negative charge also, but the direction of the magnetic force acting on it is opposite to that given by the thumb in the right-hand rule. For circular motion, the centripetal force F equals mv square over r. Here, the centripetal force is provided by the magnetic force Fb. Hence, qvb equals mv square over r. Therefore, the radius r of its circular orbit is r equals mv over qb. Summary: the magnetic force vector Fb acting on a charge q moving with a velocity vector v in a magnetic field vector b is vector Fb equals q into vector v cross vector b. For the cases when theta equals 0 degrees and theta equals 180 degrees, the magnetic force acting on the charge is 0. For the case theta equals 90 degrees, the magnetic force is maximum. Under the influence of this force, the charge performs circular motion with the magnetic field. The radius of the circular orbit is given by r equals mv over qb.